Hello, we are ALFA, a research team at CSAIL MIT. In this video, I'm introducing Lipizzaner, a GAN training framework that we have developed. Lipizzaner applies a co-evolutionary GAN training method in which it trains a population of generators against a population of discriminators to improve their robustness. It uses Gaussian mutation to optimize the hyperparameters during the training to improve the convergence. In order to improve the efficiency of the co-evolutionary GAN training, it distributes the population on a spatial grid. In turn, it applies asynchronous parallelism to speed up the training and to avoid bottlenecks. In machine learning, generative adversarial networks, or GANs, are applied to create generative models. Given a training dataset, these generative models are able to create new synthesized samples that follow the same distribution than the training dataset. GANs apply adversarial learning to train two neural networks, a generator and a discriminator, against each other. This training has shown different pathologies that limit its results. For example, mode collapse that occurs when the generator is not able to generate samples of the whole data distribution, and vanishing gradient that happens when there are no training gradients to update the network weights. In order to mitigate these issues, some authors proposed co-evolutionary GAN training, in which instead of training a generator versus a discriminator, they adversary train a population of generators versus a population of discriminators. The most common strategy is to train all discriminators versus all the generators, which provides competitive results, but it requires high computational resources. In contrast, Lipizzaner defines a spatial grid and distributes the populations on the cells of this grid. Then it defines different subpopulations according to the Moore's neighborhood. These subpopulations co-evolve in parallel. Besides, they exchange individuals with the neighbors after each training epoch. At the end, each cell returns a mixture of generators and a mixture of discriminators. The main features of Lipizzaner are fast convergence because it applies gradient-based training steps. Improved convergence because it evolves the hyperparameters to optimize the training process. The samples generated are diverse because they are created by a mixture of generators. The spatial distribution of the cells and the parallelism provide high scalability. The results show that the method applied by Lipizzaner is robust and resilient to the training pathologies. Finally, the code is freely available and can be used to address countless problems. Thank you for watching this video. If you want more information, please visit the project website.